couple of joules, but I'm going to charge up to about 2,000 volts. This is my little version of a magnet coil, sat here on this magnet rod. I'm going to leave it outside so I don't damage your ceiling.
Yeah.
And
Just gonna sneak back
I'm
through.
going to take this. This is just an aluminium, bit of an aluminium funnel, and I'm going to sit it on the top of my magnet. And this will give you an idea of some of the challenges of doing high field measurements. So,
Should we stash our credit cards?
give me your credit cards, pen numbers. I'll look after them.
So I've got a question that occurs to me. So as you're
Is this legal? No. Is this
I
safe?
don't
Where's
care.
the IWD?
so as you're how in the hell do you take measurements and not have like the wires and stuff conveying that data? Because you're sure as hell gonna use
Let's
a
see
flash.
this first, and then. Okay.
Take the power out, aren't you?
Am I supposed to be watching that?
Sometimes it attracts lightning. No. Okay, so this is just a counter. Unfortunately, some of the LEDs are broken, but it will give us some idea of what's going on. And this is my little trigger button, so I can press fire, and charge the max. So.
Reminds me of my stereo.
There you go. Some homemade Heath Robinson thing. Okay, so what we've got in here are a couple of relatively small capacitors compared to what we use in our capacitor bank. Bear in mind, we normally have a capacitor bank we're charging to about 10,000 volts, and it's the size of this room. This is about 2,000 volts and only a couple of joules, not megajoules. When I press and hold the button, this thing will say, it should say C because it's charging. And I'm going to sit there charging for a while, and then it's going to count down from 5 to 1, and at that point there'll be a little spark in this corner as it releases the current, and it pulses the magnet coil over there. So that could be a 3, 2, 1. So
Do it again.
do it again.
Do it again! Do it
And
again!
then we'll talk about why that means that our measurements are particularly challenging. It is, yeah. I mean, I made holes in the ceiling tiles at the school I was at today. So the last thing I need to do is hit like a sprinkler head, and then we'll all okay, so. Right, so that's probably charged long enough. 5, 4, 3, 2, maybe.
1. Boom.
Okay, so. So let me explain a little bit about what's happened. Plug it before it causes any problems.
You tried that with your dogs. Cats.
I've done it with my children. Okay, so
Is that a coil?
here's what. The flat bit in the bottom is a pancake-shaped coil.
Okay.
The stick that's stuck
Just
up.
a stick.
Not just the stick. So it's actually it's basically a metallic stick, and it helps focus the field. So if I took a very flat magnet coil, the field lines wrap around very tightly. By putting a high permeability material, the field lines extend up a long way, and so give the thing a kick for longer. So I get a decent launcher, not just that. Okay, but yes, that's basically a miniature version of what I do with this magnet. Is I'm discharging current through the coil to generate a pulse of magnetic field.
So this is how they're starting to launch airplanes off with aircraft carriers.
Yes, exactly. Railgun systems, or even magnetic weapons to launch them. I think someone's calculated that a generator system, if we put a railgun up the side of Pareto, we could put CubeSats into orbit. I'm not sure anyone wants that sonic boom. There you go. Okay, so why is it doing that? So this is actually one of, I like this demo probably even more than this. So this is just a bit of copper pipe, like you see in your home. This is one of these super strong, like pinch my finger magnets. It's a reasonably tight fit inside. And so what I said to the kids in school today when we're doing this, and I hope it doesn't get wedged because the magnet's a little bit of a tight fit, is use your eyes and your ears when I do this experiment. So I'm going to drop it in the top, and you guys can listen to what happens as it falls through. You hear anything? Do you see it going down?
I see it. I see it
It's
going
going super slow. Don't hear anything, because it's not hitting the sides. What I'll do is I'll pass this around, and you're free to wipe your own credit cards with this. But basically it falls through the middle and it keeps itself away from the wall. So copper, as we know, put it on the table, isn't magnetic. It doesn't stick to the magnet. But the changing magnetic field, the moving magnet, is inducing currents in the nearby conductor that have the opposite magnetic field, and so it's retarding its motion as it falls. That's essentially the challenge of doing a measurement in a transient magnetic field or a pulse magnetic field, is that the pulse, the changing magnetic field, is inducing currents in nearby conductors. And so we spend a lot of time making sure that our conductors are really small, that we don't have large loop area, because the changing flux through that loop generates big voltages of currents. I'll pass this around and you guys can play with it. So I love just watching this float down the middle of the thing. I can do it with, this thing's a slide, and you can slide magnets down different materials and actually see. So I'll tell you what, I'll pass this around and I'll get the slides out. So that's what's happening there, is that the magnetic field pulse is inducing currents around that ring of aluminium. Aluminium is good because it's a good conductor and it's light, so it flies a long way. And basically that's creating the opposite pole of magnetic field, and it's wanting to repulse and push itself apart. But I'll tell you what, I'll get the... There it is, here. I think the problem with this is that where the tube has been cut, so you can see it, there's some little jagged bits, and these magnets are a rather tight fit, so they get stuck every now and then.
Put two together, they don't get stuck.
They don't get stuck. See, Long
Figure
knows
that
what
out
she's
today.
doing. Okay, so we can equally have races here. So, these are two of these super strong magnets. We've got a whole load of different materials, from copper, which is a pretty good conductor, to plastic, which is a lousy conductor. If I put my magnet on here, it just slides down. The better the conductor, the slower it slides. So if I put it on there, you can see it's like it's moving through molasses, and it's moving really slowly. So that's the bit of magnetism that we don't experience every day as kids. We get magnets sticking to other magnets or repelling other magnets. We get magnets sticking to the fridge or not sticking to other things. But these are fundamentally non-magnetic metals, and the better the conductor, the larger the induced currents when the magnetic field changes or when it moves, and therefore the larger the attractive field that's retarding its motion. So one thing you can do if you want to come up, you can take one of these and actually just, you feel it doesn't stick when you do that, but if we stroke it up and down, it's like, you can feel the resistance. So it's a rather tactile way of getting, I guess it's Faraday's law, one of Maxwell's equations, that the rate of change of magnetic field is inducing voltage. That's why motors, electric motors,
permanent magnet
generate.
motor in reverse.
Exactly. And then all these other bits of junk, I've got old motors and things that the kids can turn cranks and light bulbs and make things move. But that to me is the thing that we don't experience every day as kids, that is through fundamentally electromagnetism.
Some publication.
What if you trust people from the magnet lab to break it?
This is what we do all the time.
That I can chill my wife.
Don't drink
Look
it.
at that.
I'm not sure I want to drink it till it stops. I might break it too.
Have you made your, I wonder what you're breaking the glass. Have you made your Halloween plans?
Okay.
I wonder if I just
More
squeeze
questions?
this.
Not sure we should use this one.
Can I give you that for a sec?
No, I would be,
I could do- Yes, some tricks and magic.
Ross,
I'll tell you what I was doing.
Ross, can I get a picture of that real quick?